All right, so let's talk about Chapter 11, Training Deep Neural Networks. And so we made neural networks with just a few layers, but if you have more complicated problems, you might need a deep artificial neural network with 10 layers or more, and that can get pretty complicated. And there might be training problems, and the thing that really made me want to present this lecture here is the problem of vanishing gradients, which is real important. What might happen is the gradient is the extent to which the output changes if you change one of the weights. And often what happens is some of those weights get small, and now you can't get any information to train your model. So we'll talk about that. That's the problem of vanishing gradients. And there might be other problems like you don't have enough data, it's too slow to train, and you might overfit the training set, which when I first heard about this stuff, that was my first thought. If I have some data and then I have 1,000,000 parameters, that's far too many parameters. If I have less than 1,000,000 data points and 1,000,000 parameters, then of course you can get a perfect fit that will hit every data point, and it's not unique, and it's not obvious how you're going to get a meaningful answer when you have more parameters than data points, which almost all of these do. And now you've seen we do it by regularization. You do it by limiting it to a smooth curve, something like that. You have to make a reasonable fit through those data points you have, not letting all 1,000,000 parameters vary as much as they want to get a perfect fit, because that really would not represent the underlying trend. You'd just be fitting the noise. So we're going to talk about the exploding gradient, vanishing gradients problem, and a few other issues, but the vanishing gradients is the most interesting thing here. And here's how it works. So here's a model. You feed in an input image, you flatten it into pixels, then you have a series of hidden layers, and then you sort it into, say, various categories of things like we did before, coat, sneaker, and bag. And so now when you try to train this, so first you randomize all the weights, then you evaluate the success, then you would like to figure out what direction and how should I change all these parameters to improve the match. So you use backpropagation, you use a subset of data like 64 items, and you calculate the derivative in all these weights, so you know how much the output depends on all these weights, and now you can calculate a vector of how much which direction moving all those weights would lower the error, and you can take a step, and you repeat those steps, and you're performing gradient descent. That's the basic technique for almost all the models we're talking about here. But the problem is, suppose that after you do this, the lower levels can have the gradient get really small, where these parameters hardly matter at all anyway. Compared to these parameters, if you allow the model to learn this way, it can learn to sort of bypass one of these layers, and then you will never optimize those weights because they're having no significant effect here, and so the step vector includes not changing them any. They don't seem to matter. That's called the vanishing gradients. And that means you're not really training all the layers. You're only training the few layers that have significant gradients, and the others are just being left at some random values. So that's not good. There's also one called exploding gradients. This can happen sometimes where you have one layer where the gradient is much larger, and that would have the same effect. You'll just be focusing on those parameters and not fixing the next. In general, the problem is different layers learn at different speeds. And this was so serious that deep neural networks were considered essentially useless in the early 2000s. And like some of you have said, and I've said too, I kept running into machine learning now and then in my scientific work, and it would look promising, but it would sort of fizzle out and not go anywhere because there were these big problems that meant you couldn't really get anything done. But in 2010, they figured it out. And the problem is a saturation region. If you have, this is the output as a function of the input signal. If the signal is low, you put out 0. If the signal is high, you put out 1. In this linear region, you can train the model. But you hit the saturation level where changing the weight does not change the output, and that means you have no information about how you need to change it to fit the model. The problem is these flat saturating areas. So they developed ways to do this. First, they developed the Glorod initialization, where you carefully choose the initialized weights of each layer to hit a spot where there's a good gradient, essentially. And that is a start. And so you've got various parameters here, but it's based on the standard deviation of the output function there. And so this is one way to do it. Another issue is dying rel use. This is the rectified linear output function. Remember, the original model had Heaviside functions, where anything below 0 you'd put out 0, anything above 0 you'd put out a 1, and that was not any good at all for gradient descent because there's no gradient at all. So you had to replace it with something smoother. And the original one that was very popular and still commonly used is this rectified linear, where anything below 0 is just 0, and anything above 0 just goes linearly forever. That's what's actually used. And here, of course, as long as you don't go to this region, there's a slope there for you, and you might use a smoother function here. There's a variety of ways to make smooth functions. That's in the output function of the neuron. So what's better is to use a leaky ReLU, where instead of having it flat on the lower region, you give it a slope there too. Now there is no input that will cause it to reach a region of an extreme slope of 0 or something very high. This is better. And there are some smooth variants of this, which, just have the same property that they have some kind of smooth, reasonable slope for most of the region that matters, and they don't have a region you're going to hit very often with no slope at all, which would be the vanishing gradients. And so, if you use this special function, SCLU, for each hidden layer, it will self-normalize. Each layer's output will tend to be a mean of 0 and standard deviation of 1. What you want is every layer to contribute equally to the output. So you would like to scale the output of these layers so each one of them is contributing a sort of equal scale to everything. So mean of 0 and standard deviation of 1 everywhere. You don't have one with a standard deviation of 0.01 and one with a standard deviation of 10, because then you would just focus on that one layer that's doing all the work, and you wouldn't not be benefiting from these other layers. You want every layer to be scaled so it makes a comparable contribution to the others, and therefore you get a chance to optimize them all. Now this thing, CLU, had the ability to automatically self-normalize, but it turned out that it was far too specific. There were weird conditions for it that were hard to meet. So this one that would automatically normalize did not become popular. What became popular was batch normalization. What you do, and this is only like 8 years old, this technique, you add an extra operation before or after the activation function of each layer, which normalizes it. So you flatten the input shape just to line up the pixels, and then you do batch normalization. Then you have a dense layer doing something, then you have batch normalization. Then you have this layer do something and batch normalization. This way you make sure that every layer gets scaled to a good scale before it goes on to the next layer, and therefore the final output is getting a contribution from every layer. This can greatly improve your deep neural networks. This solves that problem of vanishing gradients, which, as I said, is the main thing in this chapter that was very valuable. And here you see, here's how they count the parameters. The input layer has no parameters to adjust. That's just getting data. But now you're going to normalize it, so that gives you some parameters. And I don't quite know how they calculate it from 784, but anyway, then you have dense layer and normalization, another dense layer and normalization, and so on. And normalization has some parameters to it. And there are some mathematical formulas explaining how you do this, but I'm not too worried about the details of it. All right, and so, all right, I'm not going to worry about the details of that, the prediction and such. Anyway, it can turn out this can be extremely effective. It can make models converge in 14 times less iterations. Of course, there's more calculation in each iteration. You have to calculate those normalization layers, but that's not very much, and it makes your model converge much faster, as you can imagine, because otherwise you waste a lot of time trying to train these layers that are only getting tiny little steps every time. All right. And there are some hyperparameters for this called momentum and axis that determine how it does this normalization. But this has become a heavily used technique in deep neural networks. All right, and there's other tricks You can clip the gradient so it doesn't go too far. And I think the rest of this we've all talked about enough. You can reuse previously trained layers. This turns out to be quite useful. And you can pre-train on a different task. And here's Microsoft Copilot, which I said, this is one of Microsoft's big products. You have a large language model that was trained on the open web, on a whole bunch of data from the web, so it's learned basically what English is, and then you feed in your data in post-processing, add it to this large language model, and now you have a customized model that will match on your company data. And this is what really most companies want. They want this. They want all the intelligence of the large language model, plus all the customization on their own data, and they want it to be private, so you know that none of this data is leaking out. And that's how they really get something that would help get their job done. All right. And there's self-supervised learning here. All right, so I don't think I'll bother with Kahoot because I didn't really copy everything. And I don't think it matters that much about these ways to speed up the gradient descent, but there are some modifications of it that go faster. But I think that's all I wanted to put in this course. I'm going to stop this recording.